let's take a look at this exam. Now this is kind of an interesting exam. So this comes from spring 2023. It's the differential equations. And you'll notice it says it's exam 1/2. Now what that means is that what would have been exam 1 ended up being canceled due to an ice storm. And so this is a little bit unusual in that it's cumulative over the topics that we would normally cover in both exam 1 and exam 2. But other than that, there's some good problems on here. And so we should work through the exam. And because it's cumulative, we threw in an extra problem. So normally we want to do 6, but now 7. That's right. We're turning it up to 7. So let's put our name on here. And of course, we're going to put answers because that's our goal. We want the answers. And let's begin. Number 1. Solve the following ODE and give your answer in the form y equals f of x. So we have 1 plus x squared times dy dx minus y is equal to x e to the arctangent x. Now I know what you're thinking. It's like, Steve wrote this problem because there's an arctangent. Well, no, I didn't write this one, but I definitely like that there's arctangent. Now, one of the first things we should do is figure out, well, what kind of problem is it? We spend so much time focusing on how to solve problems, we sometimes forget it's just as important to learn how to recognize problems. So looking at this, what are some clues? Well, we see a dy dx. We could also call that y prime, and we see y. And that's the only place where y is showing up. Well, what does that tell us? It tells us we should be thinking about the integrating factor, or we might call this a linear first order problem. All right, so if we're in that mindset, we have a very particular procedure. So I'm going to write this as y prime. So this part right here, this is our y prime. And I'm going to get the coefficient to be 1. So y prime minus 1 over 1 plus x squared times y is equal to x e to the arctangent of x over 1 plus x squared. So what happened here was everything got divided by 1 plus x squared. So don't forget to divide the other side by 1 plus x squared as well. You say, all right, well now what? Well now we look at what's in front of the y term. The y term will tell us how to handle the integrating factor. So in this case, we see this minus 1 over 1 plus x squared. So we're going to have e to the integral minus 1 over 1 plus x squared. And that's something we can integrate. So that becomes e to the minus arctangent of x. And when we're doing integrating factors, we don't need to worry about plus c. So what we should do is multiply everything by e to the minus arctangent of x. So what we get is the following. E to the minus arctangent of x times y prime minus e to the arctangent of x, minus arctangent of x over 1 plus x squared y is equal. Now notice, over here, we already have an e to the arctangent of x multiplied by e to the minus arctangent of x, cancel. We're left with x over 1 plus x squared. Okay, good, good. Now, why are we doing this? The goal of integrating factors is to make the left-hand side very easy. And in fact, we know by design that this left-hand side will always have the form of a derivative. Namely, it's the derivative of the integrating factor, e to the minus arctangent of x, times the function y. And so we have the following situation. The derivative of e to the minus arctangent of xy is equal to x over 1 plus x squared. And now we integrate, because it's easy to integrate a derivative. And the other side, hopefully, will be easy as well. So we have e to the minus arctangent of x times y is equal to, now here, it's not arctangent because there's that x upstairs. But now we say, ooh, that seems very familiar. It's like the kind of thing we've done before, because we've done things like this before. In particular, if you were to take the derivative of 1 plus x squared, upstairs would be 2x. We only have x, so we put a 2x and a half. Then we say, aha, function derivative, that tells us log. So 1/2 log 1 plus x squared. And now we do need our plus c. And so plus c. So to get y by itself, we need to move this across. And so we'll multiply by e to the positive arctangent of x. So we get that y is equal to 1/2 natural log 1 plus x squared plus some constant c times e to the arctangent of x. And we check, we have to solve the following ODE. There's no initial conditions, which means we're done. That's it. There's our answer. Wow, what a fun function. And probably not the one we were thinking of when we started this problem, but that's all right. There we go. First one done. Whew. On to the next one. Number 2. Give the general, parenthesis, implicit, solution to the following exact ODE. Now, you might say, aha, I see the word implicit. I'm probably thinking exact. I also see the word exact, which makes me think exact. So it's like, okay, wonderful. We know it's an exact ODE. And it says, make sure to indicate how you know the ODE is exact. All right, well, we have our work cut out for us. We have to solve this, and then we have to say, why does it work? Why is the ODE exact? All right, well, let's start. How do we handle exact? Well, what we do is we say there's two pieces. There's a part attached to dx, and there's a part attached to dy. And what we do is we integrate both pieces. So in this case, integrate xy squared plus 2 dx. I say, all right, we're integrating with respect to x. We treat y as a constant. So integral of x would be a 1/2 x squared. So we have a 1/2 x squared y squared, and then plus 2x. And then, of course, some constant function, which is, say, look, constant with respect to x, and that is y. Anything that depends just on y is a constant with respect to x. Okay, well, now do the other one. So that would become the integral x squared y minus 3 dy. All right, now x is a constant. Y is what we're integrating with respect to. Integral of y is a 1/2 y squared. So we have a 1/2 x squared y squared minus 3y, and then again plus some unknown function of x. All right, now we'll pause for a second and do our exactness test. When we're solving, we can compare the parts that have both x and y involved. So in this case, it's x squared y squared. So this involves both x and y. And they match. So exact. That's the key. Now there's other exactness tests. We'll talk about those in just a second, but let's go ahead and finish the problem. Now that we know it's exact, well, we kind of knew it was exact, but now that we've shown it's exact, our last part is we say, okay, the parts where they agree, that's a piece of it, 1/2 x squared y squared. Then the parts where they don't agree, we throw those in. Now when I say don't agree, only x, only y. And that's one side, and that has to equal some constant. Well, working our way through the alphabet, e. Now we just check. Well, we're after general form. We're not after initial conditions. So e is just an arbitrary constant at this point. And therefore, that's our answer. Done. Now, could you have shown exact in other ways? Generally speaking, there are sort of 3 things you can do to show exact. one thing you can do is what we did here, just check that these agree. The next thing you can do is take a look at these pieces and compare partial derivatives. So in particular, you say, well, take the derivative with respect to y of xy squared plus 2. Does this equal, question mark, the derivative with respect to x of x squared y minus 3? So notice that here, there's a dx, took the derivative with respect to y. Here there's a dy, took the derivative with respect to x. And in case you're wondering, why is he writing 2's? Those aren't 2's, those are partial symbols. It's the symbol that we use when we indicate derivative of multivariable functions. Say, okay, so when taking the derivative with respect to y, you treat x like a constant, and lo and behold, this up just a little bit here, you say, all right, that would be 2xy. Here, x is our variable, y is a constant, 2xy. These match, and therefore we see exact. Okay, that's one test. The third test, and I won't go through it, is just check your answer. So in other words, if you get to the end and you say, okay, does it work or not, plug it in. And so you take the derivative of both sides with respect to, say, x, or with respect to y, and just clean it up. And that's another way to do it. But quite frankly, this is the one I encourage you to use just because it's the simplest, it goes very quickly, and it's nice to sort of like pause on the journey and say, oh yeah, it works, okay, keep going, and life is good. Life is wonderful. Number 3, find the general form of solutions to y double prime minus 4y is equal to 12t squared. All right, so now we're into higher order differential equations. This is a second order because it involves two derivatives. And we have to ask ourselves the question, how do we go about solving this? Well, notice something here. This part, 12t squared. This makes it a non-homogeneous problem. You say, all right, well, great. So we have a process. So what's our idea? So our solution is going to look like our homogeneous solution, sometimes called the complementary solution, and then our particular solution. We start with YC. It's always a good strategy, partly because YC is very systematic, but also because YC informs YP. So what do we do? Well, now we say make the right-hand side 0. So you have y double prime minus 4y equals 0. Turn this into algebra problem because we love algebra. R squared minus 4 equals 0. Remember, the number of derivatives is the power of r. 2 derivatives, r squared. No derivatives, no r. All right, and well, solving for r, this becomes r plus 2, r minus 2 equals 0, which says r is 2 and negative 2. Now, these numbers translate into solutions because the idea is we started with a differential equation problem, turned into an algebra problem, solved the algebra problem, and then the solution gets us back to solutions to the differential equation. So namely, we see our y sub c is, well, some constant a e to the 2t plus some constant b e to the minus 2t. We know it's functions of t because that's a t. Okay, good, good. Now, to the particular solution. Say, all right, well, we have to decide what technique to use. It's not going to be a hard decision. We always want to default to method of undetermined coefficients as long as we can. And can we? Yes. Why? Well, we kind of knew going into the test, but in this case, we can see that, hey, t squared, powers of t, that's nice. It's something that can come out of a solution to a constant coefficient differential homogeneous equation. And so that says, okay, cool. So our idea, we're going to make a list. So here we go making our list. We grab all the functions that we see. Well, we don't see many. We see t squared. Now there's sort of three things we have to check. First thing, say, okay, if I see t to a number, whole number, I always have to have all the lower terms. Now in this case we see t squared, which means we also need to see t, we need to see 1. Okay, so check that you have lower powers of t. Now if t is in the exponent, like e to the t, nothing needs to be done. So when t is downstairs, t to something has to be done. Okay, then we say, are there sines and cosines? They always come in pairs. Well, in this case, there aren't any sines, cosines. Life is good. And then the last thing is compare it. Compare your list to what you see in the complementary solution. Now in the complementary solution, we see e to the 2t, e to the minus 2t. That's not in our list right now, which means no bumping. Okay, good. So what is this list doing? What we're forming here is, what is our particular solution made out of? We can now say the following. Our particular solution, y sub p, is some constant t squared plus some constant t plus some constant e. So in other words, I'm using the pieces that we figured out, and that's what my particular solution looks like. And we need to plug that into our differential equation. Well, we see a second derivative, so let's compute that. Yp prime 2ct plus d, yp double prime is 2c. So we have 2c minus 4 times c t squared plus d times t plus e is equal to 12t squared. Okay, and we'll just pause and say, where are these things coming from? This is our yp double prime. Here's our yp. All right, now the next part, we've plugged it in group. So it's a bunch of groupies here. So we're going to group by functions. So what we say, well, we see a t squared, and so this is t squared times 4c, and then we see minus 4c, excuse me, don't forget the minus, that's important. Then we see a single t, so plus t minus 4d, and then we see the constants, which is 2c minus 4e. All that has to equal 12t squared. We say, well, that says the coefficient of t squared here matches the coefficient of t squared there. So that has to be 12. This coefficient, well, there's no t over here. Or is there? There actually is sort of a secret t. It's 0t. So that has to be 0. And in a similar way, there's the constant. Well, since there's no constant, that also has to be 0. All right. Minus 4c equals 12. So that tells us c has to be negative 3. Minus 4d equals 0. D has to equal 0. Then we get to the last one. 2c, well, let's write this down. 2 times c would be minus 6 minus 4e has to equal 0. So I can move the 4e across and divide. That says e has to be equal to minus 3 halves. All right, so updating our particular solution would be minus 3t squared, 0t minus 3 halves. There we go. All right, now what's our final answer? Because after the general form, we need to add our pieces together. So we move it up to give ourselves just enough space, and we say, aha, our final answer is y is equal to a e to the 2t, b e to the minus 2t, minus 3t squared, minus 3 halves. And done. That's it. We're done. Wow, great. That was a fun problem. Isn't it wonderful when they all work? I think this is probably one of the more challenging ones, but on this exam, but not too bad. And it's just a matter of know the process, follow along, make sure you get all the steps done. Great, good. Well, let's keep going. Number 4, solve the initial value problem. Oh, an initial value problem. We've been waiting for you. Y double prime minus 2y prime plus 5y is equal to 0. Y of 0 is equal to 2, and y prime of 0 is equal to 4. All right, good. Now we see constant coefficient, linear, homogeneous. Perfect. Our favorite kind. And so we turn our differential equation, y double prime minus 2y prime plus 5y equals 0, into an algebra equation. So this becomes r squared minus 2r plus 5 equals 0. And we say, okay, let's try to factor it. Okay, well, we tried. But even if we didn't succeed, we always have the quadratic formula. All right, so r is equal to negative b, 2, plus minus square root b squared, 4, minus 4ac. So 4 times 1 times 5 is 20. All that over 2a. Well, 2 over 2 is 1. Okay, square root of 4 minus 20, that'd be negative 16. When you take the square root of a negative, you get I, which we call the imaginary number, but okay, I. So it's 4i over 2. So that would become 2i. All right, great. And those are our roots. Now, complex roots. How do complex roots become solutions? Well, complex roots involve sines and cosines. And so remember that what happens here is you have the real part and the imaginary part. And the real part, this goes into the exponential function. The imaginary part, this goes into the sine slash cosine part of the function. So we can say that our solution looks like the following. Y is equal to some constant a, e to the t cosine 2t, plus some constant b, e to the t sine of 2t. So again, that 1 is showing up in the exponent, and the 2 is showing up inside the sine and the cosine. So that's what the general form of solutions look like. Now we have to worry about initial conditions. So we have the value at 0 and the value of the derivative at 0. So let's start by taking the derivative, so we have that for reference. So we say, okay, y prime equals, and well, product rule. So here, say derivative of the first. Well, the nice thing about e to the t is the derivative of e to the t is e to the t. So a e to the t cosine 2t. Then the derivative of the second. Derivative of cosine, negative sine. Don't forget chain rule, put a 2. So minus 2a e to the t sine of 2t. Then come here, again, product rule. Derivative of the first, e to the t is e to the t. So b e to the t sine 2t. And then derivative of the second, derivative of sine cosine. Again, don't forget product rule, 2 comes out. So plus 2b e to the t cosine 2t. Now we plug in our initial conditions. So what do we have? Well, we have y of 0, which should be 2, because that's what it says. And we see cosine of 0 is 1, sine 0 is 0, e to the 0 is 1, So the second term drops out completely, and we're left with 2 equals a. We say, aha, we can solve that. A is 2. Good for us. We know how to solve that one. Y prime is 0. Well, that should be 4. All right, plug it in. E to 0 is 1, cosine 0 is 1, e to 0 is 1, sine of 0 is 0, e to 1, and that's 0, and that's 1, and that's 1. So we'll get A, and then gone, 2B. So A plus 2B. But we know what A is. A is 2. And so we can subtract. For subtract A, we'll say that 2 is 2B, or that B is 1. So, putting in our values in for A and for B, we come now to our final answer. Namely, y is equal to 2 e to the t cosine of 2t plus e to the t sine of 2t. And we're done. That's it. That's it. That's everything. Woohoo! Nice. Nice. All right. Wow. We're flying. We're halfway done. We're over halfway done. But now, the fun part. Systems. All right. On to the next problem. There. Number 5. Consider the following system of differential equations. X double prime plus y double prime is equal to t squared. X prime plus x plus y double prime plus y equals 0. Find a single one differential equation x satisfies. In particular, an equation not involving y. So we say, we've got to get down to just the one. One differential equation that only involves x. All right, great. Well, how can we do it? There's a couple things we could do, but we're going to go the method of variation of Cramer's rule, because that's very, very sort of formulaic and procedural. There are other things you can do. You can try to be like, well, I could solve for y double prime here and replace, and then we have just a single y, and then say, now that I have a single y, replace there, and just sort of just jump back and forth, and you can actually get down to the same answer. But it kind of, you have to fidget a bit, and that's not fun. So let's just do it with, as I said, our variation of Cramer's rule, and of course, our use of d. Now here, d really stands for the derivative. So derivative with respect to t. All right, so what do we have? We'll have d squared x, because it says second derivative. So d tells you how many derivatives. So second derivative, d squared. And then d squared y is equal to d squared. Then here we'll get a d times x and a 1 times x. So d plus 1 times x. And here we'll get a d squared plus 1 times y equals 0. So we've rewritten this using our d notation. And just make sure you have the right values of d, right? So the key is how many derivatives do you have? 2 derivatives, d squared. 1 derivative, d. No derivatives, 1s. And we say, all right, in matrix form, this would be written as d squared, d plus 1, d squared plus 1 times xy equals t squared 0. Okay, so we've rewritten it as a nice system. Now from here, what we're going to do is our goal is to solve for x. And we know our goal is to solve for x because it tells x here. So we say, all right, there's x. And just remember, this is the x column. That'll become important in just a second. So we're going to take the determinant of d squared, d plus 1, d squared plus 1, x is equal to, And now replace the x column with the t squared 0, d squared plus 1. All right, so we take our determinant in here, which means we have our diagonals, d squared times d squared plus 1, subtract d squared times d plus 1, x is equal to, over here, we'll have d squared plus 1 t squared, subtract d squared times 0. Okay, good. Now, well, we expand. We have d to the 4th plus d squared minus d cubed minus d squared, and that's times x. Here we'll have d squared, t squared, plus t squared, and then we'll have 0. All right, well, 0 is 0. And what happens here? Well, the d squareds cancel, and what are we left with? D to the 4th times x, so that's the 4th derivative, minus d cubed times x. That's, whoops, why did I put y? I don't know why I put y. All right, that's why you check. It's easy to make silly mistakes. So 4th derivative minus d cubed x, which is 3rd derivative, is equal to, over here, well, 2nd derivative of t squared. First derivative would be 2t, 2nd derivative would be 2. So that would be 2 plus t squared. And we found a single differential equation involving x. There's no y in sight. Life is good. That's our answer. We're done. We're done. Whew. Nice. That is nice. It's nice when things work out relatively well. This is one which we could, in theory, solve, but we don't have to. So we're not going to, because we have more problems to do. On to the next problem. Number 6. Give the general form for solutions of dx dt is equal to 9, 5, minus 6, minus 2x. All right, and remember, this is just another way of saying x prime. If you're not comfortable with that notation, just change the notation. So x prime, 9, 5, minus 6, minus 2x. Now, the first thing that you do when confronted with a problem involving a matrix is eigenvalues. And depending upon what the eigenvalues are, then we know where we go in terms of the next step. So let's not say what we're doing in the next step until we know, are we dealing with real distinct eigenvalues, repeated eigenvalues, or complex eigenvalues? Because each one is slightly different. So we're going to find 9 minus lambda, 5 minus 6 minus 2 minus lambda. And we're taking that determinant. So we'll have 9 minus lambda, minus 2 minus lambda, subtract negative 6 times 5. So let's see, that would be lambda squared, all right, minus lambda times minus lambda. And then we'll have minus 9 lambda plus 2 lambda. Minus 9 plus 2 makes minus 7. Then we have minus 18, but here we'll have plus 30. Minus 18 plus 30 makes plus 12. All right, now the question. Can we think of two numbers that multiply to 12 but add to 7? We can. In fact, it's not too hard. It becomes lambda minus 3, lambda minus 4. Right? You can check. Lambda squared, minus 4 lambda minus 3 lambda is minus 7 lambda plus 12 equals 0. So lambda is 3 and 4. So we are in distinct eigenvalues. Now, what do we do in that case? So when we have distinct eigenvalues, what we do is eigenvectors. And we have to do the eigenvector separately. So let's start with lambda equals 3. 3. Now for that, we'll subtract 3. So we have 9 minus 3 becomes 6. 5 minus 6. Minus 2 minus 3 is minus 5. And we want to find something that multiplies that and gives us 0, 0. Okay, so we sort of like, And then we're like, well, let's just do the easy thing. Easy thing is what? Well, sort of read a row backwards and flip one of the signs. So I see 5, 6, so I'll put 5, 6, and I need to flip one of the signs, so I'll put a minus in front of the 6. And you can check. 30 minus 30 minus 30 plus 30. All right, good. So there's our eigenvalue for 3. Sorry, eigenvector. And I should point out, it's not unique. If you said, oh, I put down minus 5 plus 6, great, that also works. You can scale by any number. It's still eigenvector. All right, but we're not done because we need to do 4. Okay, lambda equals 4. What do we have? Well, 9 minus 4 is 5. 5 minus 6 minus 2 minus 4 minus 6. And that needs to equal 0, 0. Okay, do we see something? Yeah, we could do again 5 minus 5. But we can also say, hey, hold on. I see what's going on here. 1 minus 1. That works great. Now we say, cool, we've got the eigenvalues, we have the eigenvectors, and so our answer has the following form. Namely, x looks like some constant a, e, eigenvalue t, eigenvector, plus some constant e, eigenvalue t, eigenvector. Okay, now that's the general form, but we're looking for, the general form. Woohoo! Nice! Which means we're done. That's it. That's our answer. Oh, that one wasn't so bad at all. Seemed a little bit scary, but it turned out it doesn't have to be scary. And, nice. Cool. Well, one more to go. Our last problem, number 7. So let A be the matrix minus 1, 3, minus 3, 5. Compute the matrix exponential e to the at and use it to find the solution to dx dt equals ax with x of 0 equals 0, 2. All right. Now, we begin, as we do with every matrix problem, what are the eigenvalues? All right, so we do minus 1 minus lambda, and 3 minus 3, 5 minus lambda, and that would become minus 1 minus lambda, 5 minus lambda, subtract, minus 3, 3. We get lambda squared, nice, and then we'll have minus 5 lambda and a plus lambda, and so that's, let's see, minus 5 plus makes minus 4 lambda, and then we have minus 5 plus 9, which makes that plus 4. Does that factor? It does. That's lambda minus 2 squared equals 0, which means repeated eigenvalues. And now we are like, yes, yes, because this is our happy place. We love repeated eigenvalues in 2x2s because we have this cool fact. E to the at is e to the lambda t times the identity matrix plus a minus lambda I times t. That's it. Now this is true for 2x2 repeated eigenvalues. There are similar statements for 3x3 if all eigenvalues are the same, but for us, this is what we need. So, what do we have? We have e to the 2t, the identity matrix 1, 0, 0, 1, plus, now here we're going to take a minus 2i, so we're thinking of lambda equals 2, so that would be minus 3, 3, minus 3, 3, t. Or, if you like, that's e to the 2t, and we'll write this as 1 minus 3t, 3t, minus 3t, 1 plus 3t. Okay, so that's part of our answer, right? Because it says find e to the at. And now the second part says, oh, use it to find the solution with an initial condition. Now, how do we do that? Well, our great aha, our solution was going to look like e to the at times x0. See, that's why we like e to the at. It's a fundamental matrix, but it's the best fundamental matrix in the sense of if you have initial conditions, it's very easy to find solutions. So that would be e to the 2t, 1 minus 3t, minus 3t, 3t, 1 plus 3t, times 0, 2. Well, that leaves us an e to the 2t in the front. Then we have 0, 6t. Then we'll have 0 and 2 plus 6t. And that's the answer. That's it. We're done. We found the solution with the right initial condition. See how quick it can be once you have the right fundamental matrix? And, of course, it helps to know what we're doing. That's why we put in our time before the test so that we knew what we were doing so we could do great. I hope that's what happened for you. I hope you did great. And if you're getting ready for a test, I hope this helps. And because we want you to do well. We want you to get past this class and go on to bigger and better things. All right, that's it. We're done. Thank you for joining me, and I hope to see you again. Bye.